So there have been two paradigms for AI. Since the 1950s, there's been the logic-inspired approach, where the essence of intelligence is seen as symbolic expressions operated on by symbolic rules, and the main problem has been reasoning. How do we get a computer to do reasoning like people do? And there's been the biologically inspired approach, which is very different. It sees the essence of intelligence as learning the connection strengths of the neural network, and the main things to focus on, at least to begin with, are learning and perception. So they're very different paradigms with very different initial goals. They have very different views of the internal representations that should be used. So the symbolic paradigm thinks that you should use symbolic expressions, and you can give these to the computer if you invent a good language to express them in. And you can, of course, get new expressions within the computer by applying rules. The biological paradigm thinks the internal representations are nothing at all like language. They're just big vectors of neural activity. And these big vectors have causal effects on other big vectors. And these vectors are going to be learned from data. So all the structure in these vectors is going to be learned from data. I'm obviously giving sort of caricatures of the two positions to emphasize how different they are. They lead to two very different ways of trying to get a computer to do what you want. So one method, which I slightly naughtily call intelligent design, is what you would call programming. It's you figure out how to solve the problem, and then you tell the computer exactly what to do. The other method is you just show the computer a lot of examples of inputs and the outputs it should produce, and you let the computer figure it out. Of course, you have to program the computer there too, but it's programmed once with some general purpose learning algorithm. That, again, is a simplification. So an example of a kind of thing that people spent 50 years trying to do with symbolic AI is take an image and describe what's in the image. So think about taking the millions of pixels in the image on the left and converting them to a string of words. It's not obvious how you'd write that program. People tried for a long time and they couldn't write that program. People doing neural nets also tried for a long time. And in the end, they managed to get a system that worked quite well, which was based on the pure learning approach. So the central question for neural nets was always, we know that big neural nets with lots of layers and nonlinear processing elements can compute complicated things. At least we believe they can. But the question is, can they learn to do it? So can you learn a task like object recognition or machine translation by taking a big net and starting from random weights and somehow training it so it changes the weights, so it changes what it computes? There's an obvious learning algorithm for such systems, which was proposed by Turing and by Selfridge and by many other people, variations of it. And the idea is you start with random weights. So this is how Turing believed human intelligence works. You start with random weights, and rewards and punishments cause you to change the connection strengths, so you eventually learn stuff. This is extremely inefficient. It will work, but it's extremely inefficient. In the 1960s, Rosenblatt introduced a fairly simple and efficient learning procedure, much more efficient than random trial and error, that could figure out how to learn the weights on features in which you extract features from the image, and then you combine the features using weights to make a decision. And he managed to show you can do some things like that, some moderately impressive things. But in perceptrons, you don't learn the features. That, again, is a simplification. Rosenblatt had all sorts of ideas about how you would learn the features, but he didn't invent backpropagation. In 1969, Minsky and Papert showed that the kinds of perceptrons that Rosenblatt had got to work were very limited in what they could do. There were some fairly simple things they were unable to do. And Minsky and Papert strongly implied that making them deeper wouldn't help, and better learning algorithms wouldn't help. That it was a basic limitation of this way of doing things. And that led to the first neural net winter. In the 1970s and the 1980s, many different groups invented the backpropagation algorithm, variations of it. And backpropagation allows a neural network to learn the feature detectors and to have multiple layers of learned feature detectors. That created a lot of excitement. It allowed neural networks, for example, to convert words into vectors that represented the meanings of the words, and they could do that just by trying to predict the next word. And it looked as if it might be able to solve tough problems like speech recognition and shape recognition. And indeed, it did do moderately well at speech recognition, and for some forms of shape recognition it did very well, like Yann LeCun's networks that read handwriting. But what I'm going to do now is explain very briefly how neural networks work. I know most of you will know this, but I just want to go over it just in case. So we make a gross idealization of a neuron, and the aim of this idealization is to get something that can learn so that we can study how you put all these things together to learn something complicated in big networks of these things. So it has some incoming weights that you can vary, or the learning algorithm will vary, and it gives an output that's just equal to its input, provided the input's over a certain amount. So that's a rectified linear neuron, which we actually didn't start using till later, but these are the kinds of neurons that work very well. And then you hook them up into a network, and you have weights on the incoming weights for each of these neurons. And as you change those incoming weights, you're changing what feature that neuron will respond to. So by learning these weights, you're learning the features. You put in a few hidden layers, and then you'd like to train it so that the output neurons do what you like. So for example, we might show it images of dogs and cats. We might like the left neuron to turn on for a dog and the right one for a cat. And the question is, how are we going to train it? So there's two kinds of learning algorithms, mainly. Oh, there's actually three, but the third one doesn't work very well. That's called reinforcement learning. There's a wonderful reductio ad absurdum of reinforcement learning called DeepMind. So that was a joke. There's supervised training, where you show the network what the output ought to be, and you adjust the weights until it produces the output you want. And for that, you need to know what the output ought to be. And there's unsupervised learning, where you take some data and you try and represent that data in the hidden layers in such a way that you can reconstruct the data, or perhaps reconstruct parts of the data. If I blank out small parts of the data, can I reconstruct them now from the hidden layers? That's the way unsupervised learning typically works in neural nets. So here's a really inefficient way to do supervised learning by using a mutation or reinforcement kind of method. What you would do is you take your neural net, you give it a typical set of examples, you'd see how well it did, you then take one weight and you change that weight slightly, and you'd see if the neural net does better or worse. If it does better, you keep that change. If it does worse, you'd throw it away. Perhaps you change in the opposite direction, and that's already a factor of 2 improvement. But this is an incredibly slow learning algorithm. It will work, but what it achieves can be achieved many, many times faster by backpropagation. So you can think of backpropagation as just an efficient version of this algorithm. So in backpropagation, instead of changing a weight and measuring what effect that has on the performance of the network, what you do is you use the fact that all of the weights of the network are inside the computer. You use that fact to compute what the effect of a weight change would be on the performance, and you do that for all of the weights in parallel. So if you have 1 million weights, you can compute for all of them in parallel what the effect of a small change in that weight would be on the performance, and then you can update them all in parallel. That has its own problems, but it'll go 1 million times faster than the previous algorithm. Many people in the press describe that as an exponential speedup. Actually, it's a linear speedup. The term exponentially is used quadratically too often. So we get to backpropagation, where you do a forward pass through the net, you look to see what the outputs are, and then using the difference between what you got and what you wanted, you do a backwards pass, which has much the same flavor as the forward pass. It's just high school calculus, or maybe first university year calculus. And you can now compute in parallel which direction you should change each weight in. And then very surprisingly, you don't have to do that for the whole training set. You just take a small batch of examples, and on that batch of examples, you compute how to change the connection strengths. And you might have got it wrong because of the quirks of that batch of examples, but you change them anyway, and then you take another batch of examples. This is called stochastic gradient descent. And I guess the major discovery of the neural net community is that stochastic gradient descent, even though it has no real right to work, actually works really well. But it works really well at scale. If you give it lots of data and big nets, it really shows its colors. However, in the 1980s, we were very, very pleased by backpropagation. It seemed to have solved the problem, and we were convinced it was going to solve everything. And it did actually do quite well at speech recognition and some forms of object recognition, but it was basically a disappointment. It didn't work nearly as well as we thought. And the real issue was why. And at the time, people had all sorts of analyses of why it didn't work, most of which were wrong. So they said, it's getting trapped in local optima. We now know that wasn't the problem. When other learning algorithms worked better than backpropagation on modest-sized data sets, most people in the machine learning community adopted the view that what you guys are trying to do is learn these deep multi-layer networks from random weights just using stochastic gradient descent. And this is crazy. It's never going to work. You're just asking for too much. There's no way you're going to get systems like this to work unless you put in quite a lot of hand engineering. You somehow wire in some prior knowledge. So linguists, for example, have been indoctrinated to believe that a lot of language is innate, and you'd never learn language without prior knowledge. In fact, they had mathematical theorems that proved you couldn't learn language without prior knowledge. My response to that is beware of mathematicians bearing theorems. So I just want to give you some really silly theories. I'm a Monty Python fan, so here's some really silly theories. The continents used to be connected and then drifted apart. And you can imagine how silly geologists thought that theory was. Great big neural nets that start with random weights and no prior knowledge can learn to do machine translation. That seemed like a very, very silly theory to many people. Just to add one more, if you take a natural remedy and you keep diluting it, the more you dilute it, the more potent it gets. And some people believe that too. So the quote at the top was taken actually from the continental drift literature. Wegener, who suggested in 1912, was kind of laughed out of town, even though he actually had very good arguments. He didn't have a good mechanism. And the geological community said, you know, we've got to keep this stuff out of the textbooks and out of the journals. It's just going to confuse people. We had our own little experience of that in the second neural net winter. So NIPS, of all conferences, declined to take a paper of mine. You don't forget those things. And like many other disappointed authors, I had a word with a friend on the program committee. And my friend on the program committee told me, well, you see, they couldn't accept this because they had 2 papers on deep learning, and they had to decide which one to accept. And they had actually accepted the other one. So they couldn't reasonably be expected to have 2 papers on the same thing in the same conference. I suggest you go to NIPS now and see whether. Yeah. Yoshua Bengio submitted a paper to ICML in about 2009. I'm not certain of the year, but it's around then. And one of the reviewers said that neural network papers had no place in a machine learning conference. So I suggest you go to ICML. CVPR, which is the leading computer vision conference, that was the most outrageous of all, I think. Jan and his co-workers submitted a paper doing semantic segmentation that beat the state of the art. It beat what the mainline computer vision people could do. It got rejected. And one of the reviewers said, this paper tells us nothing about computer vision because everything's learned. So the reviewer, like the field of computer vision at the time, was stuck in the frame of mind that the way you do computer vision is you think about the nature of the task of vision, you preferably write down some equations, You think about how to do the computations that are required to do vision, then you get some implementation of it, and then you see whether it works. The idea that you just learn everything was outside the realm of things that were worth considering. And so the reviewer basically missed the point, which was that everything was learned. He completely failed to see how that completely changed computer vision. Now, I shouldn't be too hard on those guys, because a little later on, they were very reasonable. With a bit more evidence, they suddenly flipped. So between 2005 and 2009, researchers, some of them in Canada, we make Jan an honorary Canadian because he's French, made several technical advances that allowed backpropagation to work better in feed-forward nets. They involved using unsupervised pre-training to initialize the weights before you turn on backpropagation. Things like dropping out units at random to make the whole thing much more robust, and introducing rectified linear units, which turned out to be easier to train. For us, the details of those advances are our bread and butter. We're very interested in those. But the main message is that with a few technical advances, backpropagation works amazingly well. And the main reason is because we now have lots of labeled data and a lot of convenient compute power. Inconvenient compute power isn't much use. But things like GPUs, and more recently TPUs, allow you to apply a lot of computation, and they made the huge difference. So really the deciding factor, I think, was the increase in compute power. So I think a lot of the credit for deep learning really goes to the people who collected the big databases, like Fei-Fei Li, and the people who made the computers go fast, like David Patterson and others, lots of others. So the killer app, from my point of view, was in 2009, when in my lab we got a bunch of GPUs and 2 graduate students, made them learn to do acoustic modeling. Acoustic modeling means you take something like a spectrogram and you try and figure out for the middle frame of the spectrogram which piece of which phoneme the speaker is trying to express. And in this little database we used, relatively little, there are 183 labels for which piece of which phoneme it might be. And so you pre-train a net with many layers of 2,000 hidden units. You can't pre-train the last layer because you don't know the labels yet. And you're training it just to be able to reproduce what's in the layer below. And then you turn on learning in all the layers, and it does slightly better than the state of the art, which had taken 30 years to develop. When people in speech saw that, the smart people, they realized that with more development, this stuff was going to be amazing. And my graduate students went off to various groups like MSR and IBM and Google. In particular, Navdeep Jaitley went to Google and ported the system for acoustic modeling that was developed in Toronto, fairly literally, and it came out in the Android in 2012. There was a lot of good engineering to make it run in real time, and it gave a big decrease in error rates. And at more or less the same time, all the other groups started changing the way they did speech recognition. And now all the good speech recognizers use neural nets. They're not like the neural nets we introduced initially. Neural nets have gradually eroded more and more parts of the system. Sort of putting a neural net in your system is a bit like getting gangrene. It'll gradually eat the whole system. Then in 2012, 2 other of my graduate students applied neural nets of the kind developed over many years by Yann LeCun to object recognition on a big database that Fei-Fei Li had put together with 1,000 different classes of object. And it was finally a big enough database of real images so you could show what neural nets could do, and they could do a lot. So if you looked at the results, all the computer vision systems, the standard ones, had asymptoted at about 25% error. Our system, developed by 2 graduate students, got 16% error. And then further work on neural nets like that, by 2015 it was down to 5%, and now it's down to considerably below that. So then what happened was exactly what ought to happen in science. Leaders of the computer vision community looked at this result and they said, oh, They really do work. We were wrong. Okay, we're going to switch. And within a year, they all switched. And so science finally worked like it was meant to. The last thing I want to talk about is a radically new way to do machine translation, which was introduced in 2014 by people at Google, and also in Montreal by people in Yoshua Bengio's lab. And the idea in 2014 was for each language, we're going to have a neural network. It'll be a recurrent network that is going to encode the string of words in that language, which it receives one at a time, into a big vector. I call that big vector a thought vector. The idea is that big vector captures the meaning of that string of words. Then you take that big vector and you give it to a decoder network, and the decoder network turns the big vector into a string of words in another language. And it sort of worked. And with a bit of development, it worked very well. Since 2014, one of the major pieces of development has been that when you're decoding the meaning of a sentence, what you do is you look back at the sentence you were encoding, and that's called soft attention. So each time you produce a new word, you're deciding where to look in the sentence that you're translating. That helps a lot. You also now pre-train the word embeddings, and that helps a lot. And the way the pre-training works is you take a bunch of words, and you try and reproduce these words in a deep net, but you've left out some of the words. So from these words, you have to reproduce the same words, but you have to fill in the blanks, essentially. They use things called transformers, where in this deep net, as each word goes through the net, it's looking at kind of nearby words to disambiguate what it might mean. So if you have a word like may, when it goes in, you'll get an initial vector that's sort of ambiguous between the modal and the month. But if it sees the 13th next to it, it knows pretty well it's the month. And so in the next layer, it can disambiguate that, and the meaning of that may will be the month. And those transformer nets now work really well for getting word embeddings. They also, it turns out, learn a whole lot of grammar. So all the stuff that linguists thought had to be put in innately, these neural nets are now getting in there. They're getting lots of syntactic understanding, but it's all being learned from data. If you look in the early layers of transformer nets, they know what parts of speech things are. If you look in later parts of the nets, they know how to disambiguate pronoun references. Basically, they're learning grammar the way a little kid learns grammar, just from looking at sentences. So I think that the machine translation was really the final nail in the coffin of symbolic AI. Because machine translation is the ideal task for symbolic AI. It's symbols in and it's symbols out. But it turns out if you want to do it well, inside what you need is big vectors. Okay, I have said everything I wanted to say about the history up to 2014 or so of neural nets. I've emphasized the ideology that there were these two camps and that the good guys won. It's not over yet because, of course, what we need is for neural nets now to begin to be able to explain reasoning. We can't do that yet. We're working on it. But reasoning is the last thing that people do, not the first thing. And reasoning is built on top of all this other stuff. And my view has always been, you're never going to understand reasoning until you understand all this other stuff. And now we are beginning to understand all this other stuff, and we're more or less ready to begin to understand reasoning. But reasoning just with sort of bare symbols by using rules that are expressed as other symbols, that seemed to me just hopeless. You're missing all the content. There's no meaning there. Okay. I want to talk a little bit about the future of computer vision. So convolutional neural nets have been very effective. And what convolutional neural nets do is they wire in the idea that if a feature is useful in one place, it's also going to be useful in another place. And that allows us to combine evidence from different locations to learn a shared feature detector. That is, to learn replicated feature detectors that are the same in all these places. And that's a huge win. It makes it much more data efficient. And those things Yang got working in the 1990s. They were one of the few things that worked really well in the 1990s, and they work even better now. But I don't think they're the way people do vision. I mean, I think one aspect of it that there's replicated apparatus. That's clearly true of the brain. But they don't recognize objects the same way as we do. And that leads to adversarial examples. So if I give you a big database, a convolutional neural net will do very well. It may do better than a person. But it doesn't recognize things the same way as a person does. And so I can change things in a way that will cause the convolutional neural net to change its mind, and a person can't even see the changes I've made. They're using things much more like texture and color. They're not using the geometrical relationships between objects and their parts. I'm convinced that people, the main way in which people recognize objects, they obviously use texture and color, but they're very well aware of the geometrical relationships between an object and its parts. And that geometrical relationship is completely independent of viewpoint. And that gives you something that's very robust that you should be able to train from much less data. And I actually can't resist doing a little demonstration to convince you that when you understand objects, it's not just when you're being a scientist that you use coordinate frames. It's even when you're just naively thinking about objects, you impose coordinate frames on them. And so I'm going to do a little demonstration. And you have to participate in this demonstration, otherwise it's no fun. Okay, so I want you to imagine sitting on the tabletop in front of you, there's a cube. So here's the top, here's the bottom, here's the cube. It's a wireframe cube, like this, okay? Matte black wires. And what I'm going to do with this cube is, from your point of view, there's a front, bottom, right-hand corner here, and there's top, back, left-hand corner here. Okay. And I'm going to rotate the cube so that the top, back, left-hand corner is vertically above the front, bottom, right-hand corner. So here we are. And so now I want you to hold your fingertip in space, probably your left fingertip, where the top vertex of the cube is, okay? And now, nobody's doing it. Come on. Now, with your other fingertip, I just want you to point to where the other corners of the cube are, the ones that aren't resting on the table. So there's one on the table, one vertically above it here. Where are the other corners? And you have to do it. You have to point them out. Okay? Now, I can't see what you're doing, but I know that a large number of you will have pointed out 4 other corners, because I've done this before. And now I want you to imagine a cube in the normal orientation and ask, how many corners does it have? Okay? It's got 8 corners, right? So there's 6 of these guys. And what most people do is they say here, 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 and here. What's the problem? Well, the problem is that's not a cube. What you've done is you've preserved the 4-fold rotational symmetry that a cube has, and pointed out a completely different shape. It's a completely different shape that has the same number of faces as a cube has corners, and the same number of corners as a cube have faces. It's the dual of a cube, if you substitute corners for faces, because you really like symmetries so much that you're prepared to really mangle things to preserve the symmetries. Actually, a cube has 3 edges coming down like that, and 3 edges coming up like that, and my 6 fingertips are where the corners are, okay? And people just can't see that, unless they're crystallographers or very clever. So the main point of this demo is I forced you, by doing this rotation, to use an axis for the cube. The main axis that defined the orientation of the cube was not one of the axes of the coordinate frame you usually use for a cube. And by forcing you to use an unfamiliar coordinate frame, I destroyed all your knowledge about where the parts of a cube are. You understand things relative to coordinate frames. And if I get you to impose a different coordinate frame, it's just a different object as far as you're concerned. Now, convolutional nets don't do that. And because they don't do that, I don't think they're the way people perceive shapes. We've recently managed to make neural nets do that by doing some self-supervised training. And there's an archive reference there, which if you're very quick, you could get, or you could, I'll send out a tweet about it later. And the last thing I want to say is about, not about shape recognition in particular, but about the future of neural networks. There's something very funny and very unbiological we've been doing for the last 50 years, which is we've only been using 2 timescales. That is, you have neural activities, and they change rapidly. And you have weights, and they change slowly. And that's it. But we know that in biology, synapses change at all sorts of timescales. And the question is, what happens if you now introduce more timescales? In particular, let's just introduce one more time scale, and let's say that in addition to these weights changing slowly, and that's what's going on in long-term learning, the weights have a component, the very same weights, the very same synapses, but there's an extra component that can change more rapidly and decays quite rapidly. So if you ask, where's your memory of the fact that a minute ago I put my finger on this corner here, is that in a bunch of neurons that are sitting there, sort of being active so that you can remember that? That seems unlikely. It's much more likely your memory for this is in fast modifications to the weights of the neural network that allow you to reconstruct this very rapidly and that will decay with time. So you've got a memory that's in the weights that's a short-term memory. As soon as you do that, all sorts of good things happen. You can use that to get a better optimization method, and you can use that to do something that may very well be relevant to reasoning. You can use it to allow neural networks to do true recursion. Not very deep, but true recursion. And what I mean by true recursion is, when you do the recursive call, like a relative clause in a sentence, the neural net can use all the same neurons and all the same weights that it was using for the whole sentence to process the relative clause. And of course, to do that, somehow it has to remember what was going on when it decided to process the relative clause. It has to store that somewhere. And I don't think it stores it in other neurons. I think it stores it in temporary changes to synapse strengths. And when it's finished processing the relative clause, it packages it up and says, basically it says, now what was I doing when I started doing this processing? And it can get the information back from this associative memory in the fast weights. I wanted to finish with that because the very first talk I gave in 1973 was about exactly that. I had a system that worked on a computer that had 64K of memory. I haven't got around to publishing it yet, but I think it's becoming fashionable again, so I soon will. And that's the end of my talk, and I'm out of time.